This is a lesson on energy of simple harmonic motion in the Simple Harmonic Motion in Waves unit. In a prior lesson, I had introduced the concept and equation for elastic potential energy, which you can use as another term in the conservation of energy or work energy theorem. The big idea was to, instead of thinking about the work done by a spring, think about the potential energy stored in a spring when it has been compressed or stretched. And that's how you can use it as a term in the conservation of energy theorem. When I think about conservation of energy and energy transformations in simple harmonic motion, I'm going to remind you that we are concerned only in situations with no dissipative outside forces. So there's no non-conservative work being done to take energy away from that system. Therefore, because this is true, the total energy stays constant for that oscillating mass. Whatever kinetic energy and potential energy it has, that stays constant throughout the whole time, and we will see this when we do the lab on this. Any potential energy is then transformed into kinetic energy and back again. That doesn't mean, right, that these two terms, the kinetic energy and potential energy, are the same. I'm saying the total, those two added together, stay the same. So kinetic energy could be zero sometimes and potential energy be at a maximum value, or vice versa. Potential energy be zero and kinetic energy be at a maximum value. And how I'm going to motivate this is just look at the conservation of mechanical energy for solving problems. Notice there's no work or heat term in here. There's only the kinetic and potential energy terms, and that's because there's no work done. I don't need to include that term. So what I've done is I've kind of diagrammed for you the oscillation of a mass on a spring, and it goes back and forth from a negative amplitude to a positive amplitude. I've put the model up here for a spring that's vertical. You can see that also happening here. Notice that the equilibrium position has been marked on both of them, and there is a positive and negative amplitude. So this mass goes back and forth, and when I think about total energy, I can look at a maximum displacement. So in situation 1, I'm at negative amplitude, or in situation 3, I'm at positive amplitude. When I look at both of those, the mass has come to a stop at that point. It's not going any further in that direction. It comes to a momentary, instantaneous stop, and then it turns around and goes back again. So when I look at the total energy in that situation, kinetic energy is 0, and I'm all in potential energy. We get 1/2 k x max squared, right? Potential energy, elastic, will be 1/2 k delta x squared, and we're at a maximum value. And in this situation, you can even say the change in x, the delta x, is the amplitude, and when you plug it in here, the negative sign gets squared out, so I don't have to worry if it's positive or negative. So I can see in that situation, I can relate the total energy to the maximum displacement. I can also, in the center here, notice that V equals 0 here, V equals 0 here. Through the center, it has received force from the spring. It's pulling it in or it's pushing it out, and it will reach a V max in the center here. And so all of the kinetic energy at the center in this equilibrium position 2 that's the total energy, is the kinetic energy. The potential energy is 0. The spring is not stretched out any, okay? So that's how I can relate total energy to the maximum velocity. What I know is this total energy here and this total energy here are equal to one another, and I can actually relate the amplitude to the maximum velocity. I can just say 1/2 k x max squared, or I'm going to put an a in here, a squared, equals 1/2 m v max squared. And when I simplify this equation, you can see that happens. I get a relationship between the amplitude and the maximum velocity, moderated by the spring constant and the mass. The spring constant and the mass combine together in order to form our omega. Remember, omega is the square root of k over m. And you can see that in the equation. If I divide by m on both sides and take a square root, I would have omega in there. Let me go back to a second where I'm not at a maximum position, either in terms of kinetic energy or velocity. I'm somewhere in between, and that's why I have down at the bottom points of non-zero displacement are any place else in this motion. Any place in this region and any place in this region, there's going to be a combination of both kinetic energy and potential energy. When I add those two terms together, I will still get the same value of total energy. When you see this on a graph in lab, it will maybe kind of creep you out, but be very reassuring. There's no energy loss. That total energy stays the same, and I just have transfer of that energy from kinetic to potential to kinetic to potential over again. At any point, I can put in what I know about the x at that point in time and the velocity at that point in time, and that equation will be true. So when I look at the mathematical model for this, and this is review material from a prior lesson, when I look at the mathematical model, and remember that I can model the position as a cosine function. If I pull the spring out or push the spring in to a maximum displacement and then let it go, it will oscillate. The position graph will be a cosine. So I've put that up here, and you can see how the velocity and the acceleration also oscillate. There's a sine and another cosine here. And you can see that whenever the velocity is at a 0 value, the position is at a max value, right? That's what we understand. Then it'd be potential energy max here and 0 kinetic energy. That's what we expect to happen when it's at maximum potential energy, right? No kinetic energy. At some point later, it's moving through the equilibrium position, so it's 0. The potential energy would be 0 here. And notice that I have achieved the maximum velocity down here. When I plug that into kinetic energy, I get 1/2 mv squared, so the negative sign squares out. But this will be a max value down here. And so that goes on for cycles and cycles. What I want you to know, again, is that the amplitude, this first term in front of the trig function, right? I don't care about the trig function, that first term, that will always be the maximum value for whatever function you're looking at. So when I look at velocity, notice down here, when I look at velocity, and actually I'm going to neglect the negative sign because I don't care about it. If I just want to find V max, that will equal just this amount of term, just this front term in front of that trig function. So V max equals A omega. And I can do that also with acceleration. This isn't a lecture on forces and acceleration, but along the same principle, you can see that there's the maximum acceleration. So when you're relating energy and the mathematical model, they are consistent with one another. I picked a few problems out for us to work on. Both are vertical springs, and I will talk at the end about other situations about harmonic motion, but I wanted to just apply this in the situation of a vertical spring. So it says a 1.1 kilogram object is suspended from a vertical spring whose spring constant is 120 newtons per meter. So they give me the mass, 1.1 kilograms, and they give me the spring constant, good, 120 newtons per meter. The first thing they ask is find the amount by which the spring is stretched from its unstrained length. Okay, so it's just sitting there, and I'm just going to do a free body diagram. I know that there's going to be a spring force up and the gravitational force down, which I know is mg, right? It's suspended, it's a vertical spring, and there's a mass on the end of it. So when I draw the free body diagram, I get this. And I can assign a coordinate system just to have that, plus x. So when I write out Newton's second law, the net force equals mass times acceleration. Over on this side, I get the spring force minus the gravitational force, and it's at rest. It's just sitting there. So I get the spring force equals the weight, and so I'm going to write out K delta X equals mg. That must be true. Find the amount by which the spring is stretched. So in this situation, they're asking me to find delta x, so I can solve for delta x equals mg divided by k. Notice that I know all of those values. Either they've been given in the problem, like the 1.1 and the 120, or I know gravity is just 9.8. So I'll plug that all into the equation, and when I run this through the calculator, I get delta x equals 0.08983 meters, and I'm just going to write that as 8.98 centimeters. Okay, so it's not too stiff of a spring. We stretch out 9 centimeters with a 1 kilogram block. That seems about right. So that's what they wanted to know is, and I'm going to make a note that if I put it in oscillatory motion, this now is the equilibrium position, right? When I put the mass on, the spring had been unstretched before, and so it doesn't have, and I can make it look a little bit better here. There's the mush spring without a mass on it, and there's the old equilibrium. Well, now it has a new equilibrium position when the spring is stretched out. We're not going to deal with the old equilibrium position. I don't care about it anymore. This is the new equilibrium position. So if the spring gets displaced, either stretched down or pushed up, the mass will oscillate around this new equilibrium position. Okay? So it says the object is pulled straight down, just as I suspected. It's pulled straight down by an additional distance of 0.2 meters, so 20 centimeters. So that's what they're saying is this distance that is stretched out, delta x, and I'm going to call this max, equals 0.2 meters, and this will be the new amplitude for the motion. It will never gain any more energy than when you have it stretched out and there's no velocity. So it will always go back to that spot, and it will oscillate that high on the top when it moves upward. So find the speed with which the object passes through its original position on the way up. Okay, so the way we solve this with energy, KE initial plus PE initial equals KE final plus PE final. We're calling our initial position down here, and I can mark that here in green. The initial position is when it's stretched out along this blue line. When it reaches its maximum, find the speed at which the object passes through its original position on the way up. So here, that's the final position, and we said that's equilibrium position, and we know the velocity is going to be a maximum value at that point. Okay, so the initial position, I'm going to note that there's no kinetic energy and only spring potential energy, delta x squared, and that has to equal at some point later when it goes through the original position, it has no potential energy anymore. Right? That's our new equilibrium position, so it won't have any potential energy there. It will only have kinetic energy, so I'll put that in here, v squared, and I'm going to note that that's the maximum velocity. So I'm going to simplify this equation so I can plug a number into my calculator. So the halves cancel. I'm solving for v max, so I will keep that on that side and divide by m on both sides, so I get v max squared equals k over m delta x squared. In order to find v max, I can take the square root of that term, and I'm going to note that the square root of k over m, remember that's omega. So I get the square root of k over m times delta x. I can plug all of this in, and this will be delta x, the amplitude in the second situation for part B, which is the 0.2. So let's plug numbers in. I get the square root of 120 over the mass, 1.1, and then multiply by the amplitude, which is the 0.2 meters in this situation. So when I run all of that through the calculator, I get V max equals 2.089 meters per second, and that would be the answer. And just to verify, on the prior slide, I noted that V max would equal omega A based on the mathematical model, and that's what I have here, right? This term here, K over M, and then square root, remember that's the omega, and the delta x in this situation is the amplitude for the new equilibrium position, and omega A. So that's verifies, they verify one another. The next example I called an oscillating metal sphere. A 0.6 kilogram metal sphere oscillates at the end of a vertical spring. As the spring stretches from 0.12 to 0.23 meters relative to its unstrained length, should be a parentheses there, the speed of the sphere decreases from 5.7 to 4.8 meters per second. Okay, so I'm going to set up the situation here just to help me understand what's going on. So there's a metal sphere, and it seems like it's on its way downward. They had put the metal sphere on, and it was moving downward. And there's an initial position here, and then there's some final position. And I'm going to assume, because it hasn't come to rest yet, there's going to be some bottom position that will represent the amplitude of motion, right? Because once that spring gets stretched fully, it will oscillate around a new equilibrium position. And I haven't calculated that. All I know is that the spring is just falling downward. So there's a force due to gravity on it and the spring force, but I don't think I have to worry about that because they don't give me any information about forces. It doesn't say it's stationary. I don't know the acceleration, so I'm just going to deal with energy for right now. It says, what is the spring constant of the spring? So since I said it's energy, let's write out what we know. Kinetic energy initial plus potential energy initial has to equal kinetic energy final plus potential energy final. One last thing I'm going to note before I write out all the terms here is that we're not given the initial equilibrium position or length. And what we know is our initial and final displacements are measured from that original equilibrium position, which I'll call x naught. When a mass is put on a spring and then it comes to rest, there will be a new equilibrium position, which I will call x new equals 0. This is the new equilibrium position. We're not measuring from the new equilibrium position, we're measuring from the old equilibrium position. If we were measuring from the new equilibrium position, we wouldn't have to consider gravitational potential energy in this equation because it would already be considered in the new equilibrium position. That mass has gravity acting on it and it pulls it down, and there would be a new equilibrium position. But that's not the case we have. The case we have is that these displacements are measured from the original equilibrium position. So when I consider the initial potential energy, there's going to be a spring potential energy, 1/2 k delta x initial squared, and there's going to be some sort of initial potential energy for this mass, okay? It definitely has kinetic energy in the initial position too, V initial squared. So that's all the terms initially. When the mass is up here at this blue initial, there's some sort of displacement, and it has a gravitational potential term. When it moves down, it still has some sort of kinetic energy, which I will call 1/2 mv final squared, and it has some sort of potential energy from the spring, 1/2 delta x2 squared. So, or I'll call it delta x final squared. And what I'm going to note in here, this delta H has to equal delta x2 minus delta x1. I did that because that'll give me a positive value, and that's how far that mass drops as it's in that time, right, from this position to that position. Again, if I was measuring the delta x's from the new equilibrium position, I wouldn't have to include this term. But since I am measuring it from the old position, I have to include that gravitational potential energy term. Watch out for this when you're doing problems. So I'm going to go ahead and solve. We're solving for the spring constant. So when I look at this equation, I'm going to have to do some manipulation. Let's see, x initial is smaller than x final, so I'm going to move this term over to this side to have those terms together, and I'm going to move the v final over to this side and have those terms together. So let me do that. 1/2 mv initial squared minus 1/2 mv final squared. That will give me a positive value too. The initial speed is larger than the final speed, and that will give me a positive value. I still have the plus mg delta h on here, and I will set that equal to 1/2 k delta x final squared minus 1/2 k delta x initial squared. And you can see that will also give me a positive value. X final is larger than x initial. I'm going to continue to solve. I'm solving for k in here. One thing I will do is multiply both sides by 2. That will get rid of a lot of the factors of half through here, and I'll only have a factor of 2 here. I'm going to factor 1/2 m out of these terms, or just an m, I guess, because the 2 is here. I'm going to factor an m out of those terms, and I'm going to factor the k out of that term. So I get m v initial squared minus v final squared plus 2g delta h, factoring the m out and distributing the 2 in. That has to equal k delta x final squared minus delta x initial squared. I'm solving for k, so we'll get k equals m times all this stuff, v initial squared minus v final squared plus 2g delta h, over this term here, delta x final squared minus delta x initial squared. And I can plug in numbers. The mass is 0.6. The initial velocity is 5.7, square that, minus 4.8 squared plus 2 times 9.8 times the difference of these two numbers. It'll be 0.23 minus 0.12, which you can see is 0.11. That's all on top. I'll divide on the bottom by 0.23 squared minus 0.12 squared. Notice I have to square them and then subtract them. Don't subtract them and then square them. That's not the same mathematical operation. When I run all of this through the calculator, I get k is 180.873, and the units on that will be newtons per meter. And that will be the k value. So I've solved for the spring constant. The next part says, what is the period of motion for the sphere? So when I think about period, I know that's related to the omega. Omega is 2 pi over the period. And I also know for a simple harmonic oscillator, right? This is what we have. A mass on a spring is a simple harmonic oscillator. And I can write the omega as a square root of k over m. So if I'm looking for the period, all I have to do is take 2 pi and divide by the omega. So I get 2 pi divided by the square root of k over m. Well, I have both of those values, 180 and the mass is 0.6. If you're interested, I found the omega. The omega is 17.362. And remember, that's in radians per second. And so when I plug that in here, I get the period will be equal 0.36188 seconds. So pretty quick. It's rolling back and forth. It's moving up and down vertically. It takes a little over 1/3 of a second to do that motion. So now that we understand conservation of energy and the transformation of the energy from potential to kinetic to potential in an oscillator, we can see how that can be true for other types of oscillations. For the previous problems, I only did a mass on the spring, the simple harmonic oscillator. And so you use the equation for spring potential energy. Well, this is true for an object such as a simple pendulum that goes back and forth. At one point, it has all potential energy. Up at the top here, when it reaches a maximum angle, when it gets down to the bottom, it's all kinetic energy. And then up at the top, it will have all potential energy again. For particles oscillating in like a sound wave, they oscillate back and forth. All right, they bump against each other. There's no spring attached to them, but we can model it as a spring back and forth, and they will have a maximum potential energy and a maximum kinetic energy. The same is true for a guitar string. You can see if you vibrate a guitar string back and forth, it will come to rest at the maximum amplitudes, and it will have the maximum speed through the center. Same with this slinky. Same with the quantum harmonic oscillator. And then also, even though this is moving in simple harmonic motion, if you look at the shadow of this ball over on here, you can see that it will move slowly through this area and move quickly through here. And it will also model this oscillating back and forth with the types of energy.